In this video, I'll introduce the concept of correlation. In the previous video, we considered the percent of deaths in each country that are caused by indoor air pollution and explored some variables that could be related to this percentage. We focused at first on the percent of the population of each country with access to clean cooking fuel. When we use the percent of the population with access to clean cooking fuel as a predictor for the percent of deaths that are caused by indoor air pollution, we noticed that there was a negative linear relationship between the variables. What we're going to think about now is the question of how strong the relationship is between the two variables. Intuitively, if the dots all lie close to what's called a line of best fit, then the relationship would be strong. We can make this relationship formal with the idea of correlation. I'll show you the formula for computing correlation. Even though you'll always use a computer to calculate the correlation, there are some parts of the formula that are going to be important a bit later on. We use the letter R to represent the correlation. In the computation, we think of our list of countries as ordered, country 1, country 2, and so on, all the way up to the last country. Since we want our formula to work for any number of data points, we'll call the last one country N. And to help us notate all of the countries in the list, we use the letter I to index them. So we call them country I, where I is a number that starts at 1 and goes up to N. Then we use X sub I and Y sub I to represent the coordinates of the ith country in the list. Now, we're going to compute how far the X value for the ith country is from the average X value. So we'll write X bar to represent the average X value among all of the countries, and subtract. This difference is called the deviation of X sub I from the mean. And we'll do the same thing for the Y values. And we don't want the scale of the X or Y variable to influence the correlation, so we'll divide the deviations in the X values by the standard deviation of all the X values, and do the same for the Y values. Then we add up all of these products of standardized deviations and divide by n-1 to compute their average. And this is how the correlation is computed. Let's look at some examples to illustrate correlation. Here are some data values that I just made up. Although there is a lot of variation, the overall relationship between the X and Y variables appears to be linear. That is, it lies roughly along a straight line. And it's a positive relationship, because as the X values increase, so do the Y values. It turns out that the correlation here is 0.588. If the trend were a little more clearly visible, then the correlation would increase to 0.848. And if the relationship between the variables were slightly stronger, the correlation would be 0.950. And a slightly stronger relationship has a correlation of 0.986. And if the data followed a pattern that almost perfectly matched a straight line with a positive slope, the relationship between the two variables would be very strong, and the correlation would be 0.999. And it turns out that the largest value you can have for correlation is 1. Now, what would happen if the slope of the line were a little smaller? This is still a very strong positive linear relationship. It turns out that the correlation is still 0.999. So it looks like the correlation only depends on the strength of the relationship between the two variables and not on the specific slope of the line. Now, if the linear trend the data followed had a slope of 0, it's no longer a positive linear relationship. And it turns out that the correlation would be 0. One way to think about this is that changes in the X variable don't correspond to any change in the Y variable. So there is no relationship between the variables, and we say that the variables are independent of each other. Let's look at two more examples. Here we have a negative linear relationship, and the correlation is negative 0.999. The relationship between the two variables is strong, and the correlation is close to -1. And this is still a strong negative relationship, and the correlation is still negative 0.999. As before, the correlation depended on the strength of the relationship, but not on the specific value of the slope. Now, what if the data followed a pattern like this? The pattern is very clear, and it's a very strong relationship. However, the relationship is no longer linear. It turns out that the correlation here is 0.039. So correlation is a number that is only meaningful when we're considering linear relationships. Now, let's look back at the variables we've considered in some previous videos. We were looking at the relationship between the percent of the population with access to clean cooking fuel and the percent of deaths caused by indoor air pollution, and we're wondering about the strength of the relationship between these two variables. We can measure this with correlation. First, we can see that our data follow a roughly linear trend, which is important because the correlation is only meaningful for linear associations. Correlation is a number between -1 and 1 that measures the strength of the relationship, where the values close to 1 or -1 indicate strong relationships, and values close to 0 indicate weak relationships. The correlation also tells us the direction of the relationship, with positive correlation indicating a positive relationship and negative correlation indicating a negative relationship. For the data we have here, the correlation is -0.934, and this number reflects the strong negative linear relationship between these two variables. Let's look at the other relationships we explored in the first video. Let's consider the percent of the population living below the poverty line as a predictor for the percent of deaths caused by indoor air pollution. It appears that there is a positive linear association between these two variables, so the correlation should be meaningful. The correlation here is 0.661, which suggests a moderate positive relationship between the two variables. Next, let's consider the percent of the land area that is devoted to agriculture as a predictor. It's difficult to tell if there is a linear association between these two variables, or if there is really any association at all. We can still compute the correlation, which is 0.161. So if there is a linear relationship, it would be a very weak positive relationship between the two variables. Finally, let's look at the per capita gross domestic product. As we noticed before, this scatter plot appears to show a non-linear negative association between the two variables. So even though the association appears to be strong, the non-linearity means that the correlation wouldn't tell us anything meaningful about the relationship.